Swayam Prabha. Digital India. Educated India.
Hello students, good morning. This is Professor Ravin Zugade from Department of Chemistry, Rashtrasanta Tukadoji Maharaj, Nagpur University. I welcome you all to this BSc Honours Semester 1 core course entitled Inorganic Chemistry 1. The contents of this particular course are, there are four major topics: the atomic structure, periodic properties, structure and bonding, and oxidation and reduction. So we are going to cover these four major topics in this particular module of Inorganic Chemistry 1. This is in accordance with Semester 1 syllabus of BSc Honours course as per UGC curriculum. We are going to start with the first topic, that is the atomic structure, divided into 3 lectures. So this will be the first lecture on the topic atomic structure. This lecture has been prepared under the supervision of our academic expert Professor L.J. Paliwal from the same Department of Chemistry, Rashtrasanta Tukadoji Maharaj, Nagpur University, under the project of DTH Swayam Prabha, MHRD, New Delhi. Outline of this particular lecture is the Dalton's concept and its limitations, Thomson model and its limitations, Rutherford atomic model and its limitations, Bohr's theory, success of Bohr's theory, and atomic spectrum of hydrogen atom. The story started in the year 1810 when Dalton, a British chemist, put forward a theory of his own concept of atomic model. According to Dalton's concept, the matter is made up of atoms. These atoms are indivisible particles of the matter. You must be remembering that in Indian mythology there is a name of Rishi named Kanad. Kanad was the first person to talk about this type of indivisible particles, and according to Kanad also, the matter in nature is made up of very small fine particles, but that time the word atom was not known. Dalton was the first person to introduce this particular word of atom, and according to Dalton's concept, this atom is indivisible or indestructible. Every element is made up of atoms, and the atoms of a particular element are identical with respect to all the properties. Each atom of an element has a fixed mass. So if an element is made up of 100 atoms, then the total mass of that element will be 100 times the mass of each atom. Atoms were supposed to be indestructible according to Dalton's concept. It means that it is not possible to divide the atom further into smaller particles. Atoms combine in whole number ratio, forming compounds. Now if there is a pure element, then that will be called as an element. Whereas if there is a combination of 2 or more elements, it is said to be a compound. And when a compound is formed, the atoms of various elements, they mix or combine in a fixed ratio. Then atoms undergo rearrangement during a chemical reaction. So when a compound AB is getting converted to some compound CD, then there is a rearrangement between the atoms, and the atoms gets exchanged between their partners. This is the Dalton's concept, and the theory was entirely based on these concepts put forward by Dalton in 1810. But the problem of Dalton's concept was when more and more studies in the field of physics and chemistry took place, the limitations of Dalton model came into the picture. And some of the limitations we will discuss over here. The very first problem is existence of isotopes. According to Dalton's model, the atom is made up of, or atom has a fixed mass, and every element is made up of fixed mass atoms. Now, when the discovery of isotopes took place, it was found that isotopes are the atoms having same atomic number, or they are made up of the same element, but they have different masses. So existence of isotopes was actually challenge to Dalton's concept. Second problem was no information of internal structure of atom is given by Dalton. What are the subatomic particles? How the atom is made up of various subatomic particles, or they are charged or chargeless? Everything was not covered by Dalton. And when the further studies took place, it was found that the atom is made up of very fine particles or subatomic particles. Further discoveries showed existence of these subatomic particles, like what we today say as the protons, neutrons, electrons, etc. Then existence of allotropes, which are same element with different properties. For example, we know that carbon exists in different allotropic forms like diamond, graphite, fullerenes, etc. This could not be proved on the basis of Dalton's concept. And existence of isobars. Now, isobars have same masses, but they are made up of different atoms. Now, this is actually a contradiction to Dalton's concept, because according to Dalton's concept, atom of a particular element will have a fixed mass. So different element should have different mass. But here isobars are the elements which are actually different elements, but they have got same masses. Then the next model of atomic structure came into existence because of Thomson's experiment. It was by Sir J.J. Thomson, a British chemist and physicist. He carried out some experiment. What he did, he applied a high potential between anode and cathode. Now this cathode is a heated wire, and high potential was applied between cathode and anode, which are positively charged. Cathode is a negatively charged electrode. Now when he carried out the experiment, when a high potential is applied between these two electrodes, it was observed that rays from the cathode get accelerated towards the anode, and hence he termed them as cathode rays because they originated from the cathode. There are important properties of these cathode rays. When these cathode rays incident on some fluorescent screen made up of zinc sulfide, it was found to give luminescence or fluorescence. So the portion or the part at which these rays incident, that show luminescence property. Another property of these cathode rays is that they get deflected towards the positive electrode, that is anode, when the external field is applied. It means that this has got some affinity towards the positive electrodes, and when rotor blades were put in the path of these rays, they could rotate the beam. Now these are the observations made by Sir J.J. Thomson regarding the cathode rays. On the basis of this, J.J. Thomson came up with some important conclusions. The conclusions of Thomson experiment or Thomson atomic model are: cathode rays are negatively charged as they are deflected towards the anode. Since they are getting deflected towards the anode, it means that they should possess a negative charge. Secondly, they are made up of particles with some mass because they get rotated by the rotating blades. It's clear that it is not a wave, but they are particles. They are not the rays only, but they are made up of small particles because they get rotated. Thirdly, these particles were named as electrons. So Thomson named these particles as electrons. The atoms consist of positively charged sphere according to Thomson model, with negative electrons are embedded on it or in this particular positively charged sphere. So Thomson was the first person to put forward what are subatomic particles. The electrons are the subatomic particles, whereas the second component of the atom is a positively charged sphere according to Thomson model. So if you see this particular structure, there will be a positively charged sphere and there will be equal number of electrons which are negatively charged. Overall, the atom will be electrically neutral, but it will consist of two components: the positive sphere or positively charged ball, along with the negative electrons embedded into it. This was the concept given by Thomson. This was looking something like this. If you have pudding and some plums are placed on it, so it looks something like this, and so this model or Thomson's model was also called as pudding and plums model. Further, with increase or enhancement in new experiments, further studies were carried out. One of them, or one of the very important breakthrough regarding the atomic structure, was the Rutherford's experiment by a New Zealand chemist, Ernest Rutherford. What he did, he bombarded a thin gold foil by alpha particles. Now we know that these alpha particles are positively charged particles with two positive charges, and it is equivalent to helium nucleus. So an alpha particle source was taken and a thin gold foil was placed in front of that, and this gold foil was bombarded with these alpha particles. Certain important observations were made with zinc sulfide screen around the foil. So this is entirely covered with a zinc sulfide screen. Most of the alpha particles, they passed through the foil without any deflection. So they came up like this, and very few particles deflected by a very small angle like this, and extremely few particles scattered back by large angle like this. So these are the three important observations. Most of the particles passing through the foil without deflection, very few particles getting deflected by a very small angle, and extremely few particles getting reflected or deflected back with large angles. These were the observations made by Rutherford. On the basis of these observations, Rutherford put forward the atomic model, as if you can see that most of the particles are getting passed through the foil without deflection. It means that most of the space in the atom is empty space through which the alpha particles are penetrating with a high velocity. Secondly, a few particles getting deflected, indicating that there is some repulsion with the positive charge. Like this, if you see this particular beam of alpha particles, then that is getting deflected at a very small angle. It means that there is some repulsion with some force, and since alpha particles are positively charged, it means that the force which is repelling it should be positively charged force. Thirdly, we can see that very small fraction getting reflected back like this. It means that there is some positively charged species with high mass at definite locations. So such type of positively charged species with high mass should be there. Then only this type of reflection or bouncing back is possible. These are the conclusions of Rutherford atomic model. And so what he put forward is atom is spherical with nucleus at the center. The nucleus is positively charged and the complete mass of the atom is accumulated in this particular nucleus. And since it is positively charged, there is a repulsion between the nucleus and the incoming alpha particles. Electrons are revolving around the nucleus in circular orbits like planets around the sun. We know that planets are continuously revolving around the sun. Similarly, electrons are continuously revolving around this positively charged nucleus. This was the theory of Rutherford on the basis of this experiment with alpha particles. However, the Rutherford's model also suffered from some limitations. The first limitation was if electrons revolve around the nucleus, they should experience strong force of attraction towards the nucleus. And since they are getting attractive force towards the nucleus, it means that the electrons should emit energy, emit light, lose the energy in the form of light, and it should collapse into the nucleus. This should take place if Rutherford's model is correct. It means that if you have a positively charged nucleus and an electron revolving around it, at some point the electron should lose the energy in the form of light and should collapse into the nucleus. It means that this atom will be highly unstable. However, it is observed that most of the atoms are highly stable. So stability of the atoms could not be explained on the basis of Rutherford's model. If electrons are revolving in a continuous manner, the atomic spectrum should be a continuous spectrum. So if an electron is revolving like this, then it can emit any energy. And if it can emit any energy in a continuous manner, it means that the atomic spectrum should be a continuous spectrum. But it was observed that the atomic spectrum of hydrogen atom is discrete with lines at specific wavelengths. This is actually the appearance of atomic spectrum of hydrogen. So we get lines at specific wavelengths having specific energies. So formation of this type of spectrum could not be explained on the basis of Rutherford model, and hence Rutherford model of atom was rejected. But the only component which was accepted from this was the existence of nucleus with a positive charge and entire mass concentrated at this particular location. After Rutherford, the breakthrough in the structure of atom was provided by Niels Bohr. He is a scientist from Denmark, and the Bohr's model of atom was one of the most successful atomic model in this century. Bohr proposed a new model based on quantum mechanical concept of discrete energy transaction by electrons, and this was actually an outcome of the hydrogen spectrum, which is a discrete spectrum. What Bohr suggested, according to quantum mechanics, at subatomic level, energy is best thought of occurring in discrete packets called as photons. So what quantum mechanics says, the energy transaction takes place in the form of photons and not in the form of a continuous radiation manner. Only specific energies are allowed while others are forbidden. So certain energies are allowed energies, certain energies are forbidden energies. We can best explain the discrete and continuous type of energies with this particular diagram. If you can see, this particular person is climbing on a ramp. So he can be present anywhere on the ramp and he will move continuously, whereas this person who is climbing on stairs cannot be found in between the two stairs. He can be on this particular stair or the next stair or the next stair or the next stair. There is no location in between the two stairs. This is what is called as discrete energy levels, and this is what is called as a continuous energy level. According to quantum mechanics, the energy of electron is discrete like this and not a continuous like this. So electron can be found at this level or this level or this level, and if it wants to gain energy, it should gain energy which is difference between the two energy levels. If it is not able to gain that much energy, it will remain in this particular level, or what we call as a ground state, unless and until you supply an energy equal to the difference between the ground state and excited state. It will remain in the ground state, and when it comes from higher energy level to lower energy level, it will emit the same amount of energy which it has absorbed when it goes from ground state to excited state. This was the concept used by Niels Bohr, and he put forward the atomic model. He postulated certain things, and let us see what are the postulates of Bohr's theory. According to Bohr's theory, an atom consists of centrally located positively charged nucleus, similar to Rutherford model, at which the entire mass of atom is concentrated. So this concept was taken as it is from the Rutherford theory. But the difference lies in the second postulate, that electrons are revolving around the nucleus in fixed orbits of definite radii. So electron is revolving around the nucleus but in fixed orbit. It cannot move anywhere. So the orbit has got a fixed radius. The radius of any Bohr orbit is given by a formula Rn is equal to n square h square upon 4 pi square m e square z, where n is a number, integral number like 1, 2, 3, 4. H is the Planck's constant coming from the Planck's quantum theory or quantum mechanics. Then m is the mass of electron, E is the charge on electron, and Z is the nuclear charge. So the radius is governed by these factors. So since the value of n is quantized, or it can have only integral values like 1, 2, 3, 4, this radius will be fixed values or will have fixed values. It means that the electron cannot revolve anywhere around the nucleus, but it will orbit in a particular orbit with a particular radius or a fixed radius at equidistant or at constant distance from the nucleus. This n has integral values indicating the discrete radii. Continuing with the Bohr's postulate, in the fixed orbit, the angular momentum of an electron is an integral multiple of h upon 2 pi. That is the angular momentum, which is generally represented with a letter L, which we call as equal to m into v into r. M is the mass of electron, v is the velocity, r is the radius. This should be equal to integral multiple of h upon 2 pi, that is nh upon 2 pi. It shows that only those orbits are allowed where n equal to 1, 2, 3, that is integral values. And energy of an electron is constant unless and until it is revolving in its own shell or own orbit. Hence, these orbits are called as the stationary states or stationary energy levels. So if an electron is revolving in a particular orbit, its energy is also fixed. The energy of this electron is given by minus 13.6 Z square upon n square electron volts, where Z is the nuclear charge or what we call today as atomic number, and n is again integral value. It means that this energy cannot have any value, but it will have discrete values because n has only integral values like 1, 2, 3, 4, etc. So allowed energies correspond to integral values of n. Now when an electron jumps from higher orbit to lower orbit, suppose electron is orbiting in a higher orbit, and if it jumps from higher orbit to lower orbit, then it will have to lose energy, which is the difference between the two energy levels. Similarly, if an electron goes from lower orbit to higher orbit, it will have to absorb that much energy and then it can occupy the higher orbit. It means that the absorption of energy or emission of energy should be in the presence or in the form of quanta. That is, the energies are discretely given out or absorbed. Like the difference between the two energy levels is equal to E2 minus E1. E1 is the energy of the lower orbit. E2 is the energy of the higher orbit. These are also called as stationary states. So lower stationary state and higher stationary state. Difference between the two is equal to delta E, and delta E can have only fixed values because this E2 and E1 will have fixed values depending on the value of n. And the energy difference between the two is either absorbed or given out in the form of quanta, and these quanta have got definite energy depending on the frequency nu. This h is the Planck's constant. It means that if you have an electron revolving around the nucleus in a particular orbit, now in that case, if it is revolving in its own level, it will neither emit energy nor absorb energy. It will continuously revolve in its own fixed orbit or fixed stationary state. But if we supply energy which is equal to the energy gap between the two energy levels, that is E2 minus E1. So E1 is the energy corresponding to this particular state. E2 is the energy corresponding to this particular state. Then if we supply this much energy in the form of quantum or in the form of quanta or in the form of radiation, then this electron can absorb this energy and jump into higher energy level and then starts rotating in the second energy level or higher energy level. It will remain there unless and until it is having its own fixed energy. But if it radiates energy back equal to the energy difference between again the two levels, then it will come back to ground state and it will start rotating in its previous energy level. So this is how the energy transition takes place in a discrete manner, because the energy gap between these two levels will be fixed, energy gap between these two levels will be fixed, energy gap between these two levels will be fixed, and electron can never exist in between the two levels. The success of Bohr's model is given by certain important observations which were observed after when Niels Bohr put forward the model. The first important outcome of this, the stationary states are characterized by the numbers n equal to 1, 2, 3, etc. and these were further called as principal quantum numbers because they represent the shell in which the electron is revolving around the nucleus. The radii of the stationary states are given by r equals to n square into a0. A0 is the first energy level or first state. A0 is equal to 52.9 picometer is the radius of first stationary state, and this is called as Bohr radius. Actually, the Bohr model was put forward for hydrogen atom, and hydrogen has got a single electron, and so it will revolve in the first energy level or first stationary state having the radius of 52.9 picometer. Then energy of a stationary state is given by minus RH into 1 upon n square. This RH is called as the Rydberg constant, and this Rydberg constant has a value 2.18 into 10 raised to power minus 18 joule. Hence, the energy of the first level will be equal to 2.18 into 10 raised to power minus 18 joule if we put n equal to 1 in this equation. Then Bohr's theory could be applied to hydrogen-like atoms because see, firstly the theory was put forward for hydrogen atom, but it was observed that if you have atom like helium positive ion, Li2 positive ion, which contains single electron, so this Bohr's theory could be successfully applied to the single electron atoms or ions like hydrogen atom, He positive ion, Li2 positive ion. So that was an important outcome of this or success of Bohr's theory. For other atoms with single electrons, you have En is equal to minus Rh into Z square upon N square, and this R is equal to N square A0 upon Z square. Now, for other atoms, Z will not be equal to 1. If Z equal to 1, then it is true for hydrogen atom. The energy is given by this particular formula. But if you have different atom like helium or lithium, then Z will be 2 or 3, and depending on that, the energy will go on changing and the radius will also change. So radius depends on 2-3 different factors. The first factor is the Bohr radius A0 value. Second factor, the principal quantum number n, which is integral value, and Z is the nuclear charge, or you can say the atomic number of the atom. You can see this very clearly that En is equal to negative. You will find why the negative sign is there. Now this negative is the energy with respect to free electron. Now if you have a free electron in the space, its energy will be 0. But if the electron is present in an atom, it is attracted by the positively charged nucleus, and because of the attractive forces, there is a net release of energy. Hence, the electron which is present in an atom revolving around the nucleus will have an energy which is less than the energy of the free electron, and hence the sign negative is always used to show the energy of an electron in an atom. Now we will discuss the line spectrum of hydrogen atom, which is an important outcome of or important advantage of our Bohr's theory. An important success of Bohr's theory is its ability to explain the line spectrum of hydrogen atom, which could not be explained by Thomson model or Rutherford model. According to this theory, only discrete levels are allowed. Hence, electronic transitions involve discrete energy transfers. The atomic spectrum becomes a line spectrum, as we have seen. Consider an electron present in a higher energy level E2 and it jumps to a lower energy level E1. Suppose the quantum numbers of these two levels are N2 and N1, where N2 is higher than N1. Then definitely, since the electron is jumping from higher energy level to lower energy level or higher stationary state to lower stationary state, the energy is released. And the released energy is given by delta E, which is equal to the difference between the energies of the two stationary states E2 minus E1. And this should be equal to the energy of the quantum, that is hc upon lambda, which is equal to hc into nu bar. Nu bar is the wave number and wave number is the reciprocal of the wavelength. Now according to Bohr's theory, the wave number is related to number of shell, as nu bar is equal to RH into 1 upon N1 square minus 1 upon N2 square. That is, whatever is the wave number of the emitted line, that will depend on the two quantum numbers N1 and N2, the quantum number of higher energy level from where the electron is jumping, and the quantum number of the lower energy level to which the electron is jumping. And RH is the Rydberg constant, and in terms of the wave number in meter inverse, the value of Rydberg constant is approximately 1.1 into 10 raised to power 7 meter inverse. Hence, it is possible to calculate the wave number of various emission lines obtained in the spectrum with different values of n. Now you can see that since this RH value is constant, the wave number depends only on the principal quantum number of the two energy levels between which the transition of electron is taking place. Now let us see how the emission spectrum of hydrogen will appear according to Bohr's model. The first series of lines which is obtained in the hydrogen spectrum is the Lyman series. Now what is this Lyman series? It is a series which is obtained when electron jumps from higher energy level to an energy level n equal to 1. That is the first energy level, or when the electron jumps from higher Bohr orbits to the first Bohr orbit. And this particular series or the Lyman series lies in the UV region of the spectrum or ultraviolet region of the spectrum. Now, if we try to find what is the wave number associated with this particular series, then for this series you have N1 is always equal to 1. So, nu bar will be equal to the Rydberg constant into 1 upon 1 square minus 1 upon N2 square. Now, this N2 value can be anything above 1, means N2 can be 2, 3, 4, etc. So, electron jumping from second level to first, third level to first, fourth level to first, etc. All these will lead to a series of lines called as the Lyman series of lines in the emission spectrum of hydrogen atom. So, if we see this entire emission line or emission spectrum, the wave numbers in terms or wavelength in terms or in angstrom units are given over here. So, this Lyman series is in the UV region of the spectrum of electromagnetic radiation. Second series which is obtained is called as the Balmer series. Now this series is obtained when electron jumps from higher energy level to second energy level. It means that your N1 is equal to now 2, N2 can be anything higher than 2, and this lies in the visible region of the spectrum. So for this series, the wave number of the emitted line is given by RH into 1 upon 2 square minus 1 upon N2 square. Here the values of N2 can be 3, 4, 5, etc. It means that electron is jumping from either third level to second level, or fourth level to second level, or fifth level to second level. So all of these will lead to a series of lines in the emission spectrum of hydrogen, and that series will be called as Balmer series, lying in the visible region of the spectrum. Now this is the only series which is observable in the visible region of the spectrum. Third series is a Paschen series. Now this series is obtained when electron jumps from higher energy level to a level n equal to 3. Means electron jumping from 4th, 5th, 6th, 7th Bohr's orbit to 3rd Bohr's orbit. It lies in the IR region of the spectrum. And for this, the value of nu bar is given by RH into 1 upon 3 square minus 1 upon N2 square. And here the values of N2 can be 4, 5, 6, etc. It means that electron is jumping from 4th level to 3rd level, 5th level to 3rd level, 6th level to 3rd level. All of these will lead to this particular series called as Paschen series. The fourth series is the bracket series. Now this series is obtained when electron jumps from higher energy level to 4th energy level. And similar to previous series or similar to Paschen series, this bracket series also lies in the IR region of the spectrum or infrared region of the spectrum. For this, the value of nu bar is given by RH is equal to 1 upon 4 square minus 1 upon N2 square. Now N2 is higher than 4. It means that N2 can have values 5, 6, 7, etc. Meaning that electron jumping from 5th shell to 4th shell or 5th stationary state to 4th stationary state, 6th to 4th, 7th to 4th, etc. will lead to this bracket series of lines. Next series is the Fund series. Now this Fund series is obtained when electron jumps from higher orbitals or higher Bohr orbits to the 5th Bohr orbit. It means that your N1 is equal to now 5 and N2 can be anything higher than 5. You can have this N2 value infinity also. So 6, 7, 8 up to infinity. You can have any value. So electron can jump from outer space into the 5th level, that is infinity to 5. Then the last series is the Humphrey series. Now this series is obtained when electron jumps to energy level n equal to 6. It again lies in the IR region of the spectrum. And for this nu bar value will be Rydberg constant multiplied by 1 upon 6 square minus 1 upon N2 square, and N2 can have values 7, 8, 9, etc. in this particular case. Now, if we try to correlate whatever we have obtained from on the basis of Bohr's theory, Lyman series, Balmer series, Paschen series, bracket series, Fund series and Humphrey series. Now you can see this Lyman series is obtained when electron from anywhere is jumping to first energy level, and this series is obtained in the UV region of the spectrum, and the energies are, or the wavelengths are of the order of 100 nanometers. And we can see that this complete series of lines is obtained as very closely spaced lines, and these are called as Lyman lines. The first Lyman line is called as Lyman alpha, which is obtained when the electron is jumping from second energy level to first energy level. And then the next one, they go on left side with decrease in the wavelength with increase in the energy gap between the energy levels. Similarly, when we come to the Balmer series, this is the only series which lies in the visible region of the spectrum, and the electron is jumping from third to second, fourth to second, fifth to second, and so on. So electron is landing into second energy level, then it is called as a Balmer series. Electron landing into third energy level is called as Paschen series. Electron landing up into the fourth energy level is bracket series. Electron landing up into the fifth energy level is Fund series, and electron landing up into the sixth energy level, that is a Humphrey series. We can have many more series like this, but these are the commonly observed series in the hydrogen spectrum, or we can say the emission spectrum of hydrogen. Now out of this is only in the visible region. This Lyman series is in the UV region of the spectrum, whereas the remaining series which are on this side are having lower energies, and they are in the IR region of the spectrum or infrared region of the spectrum. Now till now what we have seen are the success of Bohr's theory. So it was very successful in explaining various properties of atom, and especially the emission spectrum of hydrogen and hydrogen-like atoms. But even after this, Bohr's theory suffers from certain limitations, and we are going to discuss these limitations in brief. The very first limitation is because of the Heisenberg's uncertainty principle. Now what this Heisenberg's uncertainty principle says? It states that the electrons which are moving in various orbits according to Bohr's theory, it is impossible to determine their position and momentum simultaneously. It means that according to Heisenberg's uncertainty principle, there is always some uncertainty involved in the position of the electrons. And since there is uncertainty in the position, the fundamental concept of Bohr's theory that electrons are revolving in the various fixed orbits is completely ruled out by this particular principle. Since according to Bohr's theory, electron is revolving in a definite orbit with fixed path. But according to Heisenberg uncertainty principle, there is no fixed path for electron. There is always some probability of finding the electron outside this path. So the concept of fixed orbit has been completely ruled out by this principle. Second problem of Bohr's theory was it could explain or very well explain the emission spectra of hydrogen or hydrogen-like atoms which contain only single electron. But it could not be applied to multi-electron atoms, even helium atom or lithium atom, the simple atoms containing 2 or 3 electrons. The spectra of such atoms or multi-electrons atom could not be explained on the basis of Bohr's theory. So Bohr's theory failed over there, you can say. Thirdly, it was observed that when a high resolution atomic spectrum is obtained, then under high resolution, the lines which are obtained in the Lyman series, Balmer series, Paschen series, etc., they get split up into multiplets, that is doublets, triplets, etc. So why these multiplets are obtained? Because according to Bohr's theory, we have seen that there are fixed orbits, and if an electron jumps from lower orbit to higher orbit, then a fixed amount of energy has to be absorbed from the electromagnetic spectrum. And if the amount of energy absorbed is fixed, it means that we should get line at a fixed wavelength. But it has been observed that these lines are not singlets, but they are multiplets actually. So this could not be explained on the basis of Bohr's theory. Fourthly, an important effect called as Zeeman effect is observed when the hydrogen spectrum is observed in the presence of external magnetic field. Now when an external magnetic field is applied, the spectral lines get split up into multiplets. Now, why these lines are getting split up in the presence of external magnetic field could not be explained on the basis of Bohr's theory, because Bohr's theory still says that the electrons are revolving around the nucleus in fixed orbits. And next is the same effect or similar effect of splitting of the spectral lines in the presence of external electric field is also observed, and this is called as Stark effect. So this Zeeman effect and Stark effect, one is in the presence of external magnetic field, second is in the presence of external electric field. Both of these effects could not be explained on the basis of Bohr's theory. So that both of these are important limitations of Bohr's model of atom. And last one is the Bohr's theory is unable to explain the bonding between atoms to form molecules. We know that atoms have a tendency, or atoms are generally unstable, and they are always present in the form of molecules. So they have a tendency to undergo bonding. So why the bonding is formed between the atoms, identical atoms or non-identical atoms, similar atoms or dissimilar atoms, why the bonding is taking place and how the bonding is taking place, both of these could not be explained on the basis of Bohr's theory. So these are the important limitations of Bohr's atomic model. So the summary of this particular lecture we will just go through very rapidly. First one, we have discussed various atomic models proposed by Dalton, Thomson, Rutherford and Bohr. Apart from these, there were many more models, but these are the prominent models which which have been proved to be extremely important milestones in the success of this science, mainly physics and chemistry. Dalton's model starting in the early 19th century and Bohr's model early 20th century. So it's a journey of 100 years. Then each theory led to some advancement in the available knowledge about atom. So some new inventions, some new discoveries led to new theories. Bohr's theory was the most successful among them. Quite obviously, it could explain various observable properties of atom, including the special important property of the emission spectrum and the quantum mechanical treatment given by Bohr's model. It led to better understanding of atom and subatomic particles. So these are the contents we have discussed in this particular lecture. This is all about this particular lecture. We will continue this topic in the next lecture number 2. Thank you. Thank you very much.